So this is joint work with Howie Shrobe at MIT, funded by the Office of Naval Research. It's not responsible for its contents. So I think we can all agree that domain expertise is essential both to human and machine intelligence. And that holds across all aspects of cognition. But in this talk, I'm going to focus on sequential goal-directed activities. And people regularly use knowledge about activities to carry out complex procedures that are still very routine, right? Driving to work, making breakfast. They do this to achieve their goals, but they bring their knowledge to bear in a very focused way. Now, this isn't a new idea. It goes back probably farther than this, but at least to Miller, Galanter, and Pribram's book, Plans and the Structure of Behavior, where they talked about these kinds of mental structures that we use to carry out routines. They called them plans. That's not the modern sense of plans that you find in the AI community, but that's what I'm going to be focusing on here today. And I'm going to talk about a new approach to procedural expertise, to representing it and to using it, that we call hierarchical problem networks. Now, what we want is a theory of procedural expertise that explains what the major features of human problem solving. I'm sure I've left some out, but here's the 5 that I'm going to focus on. We want to be able to generate novel action sequences that achieve a collection of goals. We want to consider both goals and situations when selecting actions. We want to decompose complex activities into simpler ones when that's needed. Use knowledge to guide or to constrain search when it's available, but when it's not, or when it's parts of it are missing, to fall back on problem space search if that's necessary. Now, there are existing frameworks for knowledge-based planning that handle these things, but they also have limitations. So let me go over a couple of them. The first and best known is hierarchical task networks, where knowledge about planning relevant knowledge is encoded as a set of methods. Each method has a task name and arguments. It's basically like a goal to do something, right? To drive to work or to make an omelet. So the task name with arguments for each method. Each method also states the conditions about the current state under which that method will apply. If it's not satisfied, then you should not use that method. And then if the conditions are satisfied, then you can decompose that task into a set of ordered subtasks and so on. So these kinds of knowledge structures can encode conditional, disjunctive, and even recursive procedures. And they're not just useful for plan generation. They also can be used for plan execution and for plan understanding. And they have been used for all of those. Now, there's a related class of framework called hierarchical goal networks, or HGNs. They're very similar. The big difference is, at least in most versions of HGNs, that the method specifies in the head of each method the goal that it will achieve. It's not a specific goal, it's a generalized goal, like a predicate with some arguments. It has conditions on the state under which that method applies, just like in HGNs. But rather than decomposing into subtasks, it now decomposes into sub-goals. So these cannot represent as arbitrary procedures as HTNs. HTNs can encode a procedure where you start you start standing somewhere and you turn a circle, and when you're done, you're back where you started. That is not a classic planning task. HTNs can handle that. HGNs have a more difficulty with that. But they do support goal-directed processing much more directly, and I think more intuitively. And both of them have mappings to classic procedural programming languages. They have things that are sort of like subroutines, but they encode them with very modular relational notations like you would find in classic AI. Now, despite their strength, both HTNs and HGNs have an issue. They can't state general procedures for problems that involve goal interactions. Now, when I say they cannot do that, I mean sort of the traditional or classic HTNs and HGNs. There are extensions to them in various types that I cite in the paper, and that the reviewers pointed out, that where you can augment them to get goal interactions, but the basic approach where you just have a set of these methods cannot handle that, as far as I can tell, or other people I've talked to. For example, if you want to have an HTN for building towers in the blocks world, suppose you want to have a single program, a set of methods that will build, you have built a tower with 2 blocks or 3 blocks or 5 blocks. You're going to need a separate method for each number of blocks. Right? There's variable arguments, so it can be different blocks, but you have to have a method that talks about how many blocks there are. That does not sound to me like a general procedure. You can write a more general HGN program that doesn't tell you how many blocks are in the tower. It's in the goal information, but then the HGN solver is going to have to carry out search to try out different heights of blocks to see whether it gets all the goals. So now HGNs have the same issue. They need one method for each type of tower because they cannot encode knowledge about goal orderings. And we've got a new framework, hierarchical problem networks, that overcomes this limitation. So now let me tell you about that. I call it a theory because it's got a set of theoretical assumptions or postulates. The first 5 are going to be very familiar. They're nothing new. You have a state is a set of relational facts that describe a situation. A goal is some desired relation. And a problem, in this case, is a set of goals. It's not a initial state and a set of goals. I'm going to call a problem just the set of goals itself. And that turns out to be very, very useful in this scheme. A hierarchical plan is a recursive decomposition of a problem into subproblems that terminates in primitive actions, operators. Again, procedural knowledge is a set of methods that specify how to do that decomposition. And again, each method has a set of state-related conditions under which it's acceptable to carry out that decomposition. Now, this is nothing new, okay? You find this in HTNs and HGNs. This is closer to HGNs because the methods talk about goals. They don't talk about tasks. What's new are these, that each method, each HPN method, tells you how to decompose an entire problem, which is a set of goals, into an ordered set of subproblems, which are themselves sets of goals. They might be singleton goals, but it's still a set. Second, each method specifies goal-related conditions under which a decomposition is not acceptable. Basically, it says, if you have this goal in your problem and it is not yet satisfied, do not use this decomposition. And finally, there's something about the structure of these methods. Each method's head is the effect of some primitive operator, O. And then there's 2 subproblems. The first is to achieve the preconditions of O, and the second is to actually apply O. Now, if that sounds a little bit like GPS and means ends analysis, it is related, but this is a knowledge-based version of it, right? So we've codified how to do that for particular problems or subproblems. And you'll see in a minute, these 3 structural constraints give hierarchical problem networks a very different feel from HGNs or even HGNs. In fact, they come closer to something like generalized partial order plans, and that lets them they can handle tasks with arbitrary numbers of objects. So here's an example for the blocks world. This is a hierarchical problem network that I wrote by hand for the blocks world. It only has 6 methods, and I won't go through them all. I'll just go through. If you look at one of the methods, at the first one, Again, each method has a head, a set of state conditions, an ordered set of subproblems, and an optional set of these goal conditions. So let's look at that first one. It says if you have a problem that includes the goal on X, Y, okay, and it's not achieved yet, so you wouldn't try this if it was already achieved, and X is a block and Y is a block, then you can create two subproblems. The first is to make sure that X is clear and that Y is clear and that you're holding X. And then once that's true, then you want to stack X on Y. Now, in fact, that's not the entire decomposition, because that's only going to do address part of the current problem, right? There's still everything else. And so as you'll see in a second, this actually leads to a decomposition to three subproblems, but the method itself only talks about the first two. Now, the important bit is that final thing, that unless goals condition right here. And that says you can do all this if these things are true, unless you have a goal, an unsatisfied goal to get Y on any other block, or you have an unsatisfied goal to get Y on the table. If those are if you do have such an unsatisfied goal, you better not do this yet, because you're just going to have to undo it later, right? This is the notion of condition clobbering in partial order plans, except here it's encoded in a very simple, pithy formalism for talking about this stuff. Okay, so then there's operators. The operators are nothing special. They are very similar to strips or PDDL operators. The only thing is that they have a head that refers to the name and arguments of the operator, and so they are treated as methods, but they're always going to end up being terminal nodes in any hierarchical plan. So I won't spend more time on that. This is more interesting though. So let's look at a simple hierarchical plan for the blocks world. Let's suppose that the problem we're working on, we want to get, well, we start off with we got we got 4 blocks, and they are all on the table, and we want to get A on B, and they're all clear, and we want to get, and our goal is to get A on B, B on C, and we want C on the table. You can ignore D. Okay, now if you think about this, they're all on the table. You know what to do, right? You don't put A on B first, because you're gonna have to undo it so that you can get B on C. And so what happens here? This is a hierarchical plan, and so each non-terminal problem. This is the top level problem here, in the first line. From above, there are 3 subproblems. The first is to get C clear and be holding B, because that's the conditions of the second subproblem, which is to apply stack BC. And the third problem is everything else in the original problem that doesn't handle, right? So you still need to get C on the table and A on B. And then there's this recursive structure, right? So to do this, there's 3 subproblems. The middle one is to pick up B, and here's pick up A, and here's stack AB. Now look at this last one here. This is subproblem on table C. There's no decomposition there because it's already satisfied by the time you get there. Now this plan is right branching, but you can have left branching and mixed branching hierarchical plans as well. And I could give you examples, but I don't have time. Okay, so the hierarchical networks also make assumptions about processing, that planning involves the recursive decomposition of problems into subproblems, that planning iteratively, there's a problem stack, which I didn't tell you about. It's like a goal stack, but it's not a goal stack, it's a problem stack, a set of goals. That planning iteratively examines the top element on the problem stack, and then it can either pop it or place new subproblems above it. problem decomposition has three main sub-processes: method matching, method selection, and then method expansion. And planning, if you don't have enough knowledge, then planning involves, planning involves search through a space of decompositions defined by the methods, the problem goals, and the initial state. There's always search. It's just that often, if you have the right knowledge, you never have to backtrack, right? So the system doesn't realize it's searching, but it sort of is. Now, these aren't really exciting because they're pretty much shared with HGNs and HGNs. The key difference between the frameworks is not the processing, it's the representation. Now, so we've implemented a planner that embodies these postulates. There's a control cycle, and there's really four conditions. If the topmost problem matches the current state, then you pop it. Unless it's the top one, then you're done. That you pop that problem. If not, then if the topmost problem is to apply an operator, O, and O's conditions are satisfied in the current state, then you apply it and update the state. And you also pop it. If not, then if you have a method that applies to the topmost problem, then find its subproblems, push them onto the stack, and add them to the hierarchical plan. Add them as children. And of course, if the plan is too long, or if you can't find a method that applies, then you pop the current problem and you backtrack. That's it. It's a very simple technique. And again, given the appropriate knowledge, this will mimic a deterministic procedure. That's not quite right, because sometimes there's choices that don't matter. So you could do it this way or this way, but there's still no search. But it's effectively deterministic, and it only searches when it needs to. Okay, so I'm going to give you another example to clarify the key idea here. And I know it's going to seem simple, but I assure you, at least from what I've seen, it's a simple change with big implications. So let's go back to that first method from the table for getting one block on. So you want to get, if you have a goal to get X on Y, and X and Y are blocks, then you can create two subproblems. The first is to have clear Y and holding X both be true. And those are the conditions of the second subproblem, which is to apply stack XY. Unless you have these unsatisfied goals of this form on Y any or on table Y. Now, let's suppose the top problem is you want on AB and on BC. Okay. And the state is what we saw before. The blocks are on the table and they're all clear. Now, the head of this rule, this method, matches in two ways, right? It can match against the unsatisfied goal on AB with X bound to A and Y bound to B, or on BC with X bound to B and Y bound to C. But the first match is going to fail. Why? Because there is an unsatisfied goal on BC that blocks it. So that keeps it from happening. That means that the second match can apply, and after you've achieved that, after you've achieved on BC, then this rule can then you can instantiate it with on BC instead. And that's how this framework achieves goal ordering effect. Okay. So we want to demonstrate the HPD. Stands for Hierarchical Problem Decomposer. So we built knowledge bases for 3 planning domains. And I did these by hand. Okay, there's no learning in here yet. One's for blocks world, which you're all familiar with. One is for logistics planning, which involves transporting packages from initial to target locations. And one is for a domain called depots. These have all been well studied in the AI planning literature. And the only thing that's really interesting here is I want you to look at how many methods there are for each of these. Okay. Now, I don't have proofs that these are complete in the sense that they will solve any problem in these domains with no search. But in fact, when we ran them on a suite of problems, 10 for 10 for logistics and depots, 20 for blocks world, they did find hierarchical plans with no search. And some of these were up to 18 steps long, right? So these are not all, some are trivial, some of them are definitely not trivial. And so the argument is that that HPNs can represent general procedures very effectively with very few methods. There's something about this representation that leads to a kind of compactness, and that surprised me when we first came across it. So we also did some lesion studies to try and understand the source of the power. And so this is a plot where we compared, we ran the system in two conditions. One where for each of the domains, it had all of the methods had all of the conditions, both the state related conditions and the goal related conditions. And then we also compared that on the same problems to a version of the knowledge base that only had the state conditions, did not have the goal conditions. Okay? And you can see that anything above the diagonal means that the complete knowledge base, the one with the goal conditions, took less time. This is CPU time, and it's it's log of CPU time. So,
hey Pat, just a time warning. You have just under 4 minutes now.
Right. Thank you. And so you can see that there's almost always this helps. I think the ones below the line are probably just due to averaging. Each of these is averaged over 30 runs. This is a scatter plot where we did the other thing where we ran the system with complete knowledge and compared it to a version that only had the goal conditions. You see here that that's actually much worse. It looks like the state conditions are actually doing more of the heavy lifting in all three of these domains. And that was interesting. And that led to some additional studies where we looked at scaling effects. This is just blocks world, and we looked at 4 versions of the system, of the knowledge base, where you had both kinds of conditions, just state, just goal, and neither. And you see that as you increase the number of irrelevant blocks, we held the number of goals constant, that the state conditions are really unaffected by that. So that means this is because they're in charge of selecting variable bindings. But the goal conditions help not at all. It's basically might not be there. And here's where we did the same kind of thing, where we held constant the number of blocks. Did we? Yeah. But we varied the number of interacting goals, basically the height of the tower that you want to build. And it looks like, and again, this is on log scale. So this is actually growing a little bit faster than linearly, for reasons that we can discuss offline. But the other stuff is growing a lot faster. The state only and goal only are comparable until you get to about 6 interacting goals, and they cross over. And here you see that the goal conditions are really making a big difference. Not as much as we have of both, though. All right. There is a lot of relation to previous research, and I talk about this in paper, and I'm not going to spend time on it here. What I really want to do is to show you the consumer reports table that one of the reviewers suggested, and I thought this was a great idea. So thank you, whoever did that. So this shows 4 planning frameworks: classic planners, HTNs, HGNs, and HPNs, and how they compare. They can all generate sequential plans that achieve goals. These 3 on the right decompose complex activities hierarchically, and the methods have conditions on the states. HGNs and HPNs index the methods by the goals that they achieve. But HPNs have these 3 unique properties. They decompose problems into subproblems. They have methods require certain goals be unsatisfied. Require that certain goals not be unsatisfied. And the methods are themselves linked to primitive. Every method is linked to a primitive operator, and that leads to a particular programming style that's unusual, but very compact. So in future work, we are planning to to augment this in various ways. I want to stick in heuristics that favor methods that have fewer unsatisfied goals in the first subproblem. I think that will reduce reliance on the state conditions. We want to support non-deterministic outcomes, actions that can have more than one outcome. You really need that for information gathering operations and things like diagnosis. We want to add derivative operators that have temporal constraints. You need that for domains like cooking where you have parallel actions. And I really want to integrate HPN problem solving with partial order planning, where if you do not have them right now, you have to have the methods, but they might not have all the conditions they need. But what if you don't even have the method? Well, you can use partial order planning to in its stead and chain backward that way. And I believe that last extension holds the key to how we can learn these, to learn both the state and goal conditions on HPNs. And I think we can do it analytically, but you have to wait until next year and come back and hear about those results if it works out. Here's a summary, but if I'm out of time, we can stop and ask questions.
It looks like, thank you so much, Pat. Looks like there are a few questions in the Slack. Do you have access to the Slack, or do you want me to read the questions to you?
I do. If I look at them, then I get to pick and choose. But oh, there they are. Okay. HGNs can support turning around if there's a representation of time. Yes, I knew that. We thought about that when we were doing it with Icarus, but it's a good point. You have to extend. You have to have a temporal representation. David Eha, a key contribution is the explicit relation of goals. Nice relations may be of interest, such as concurrent goal pursuit. I'm open to that. And so David Eha is one of the leaders of the goal reasoning community. So he would ask a hard question like this. I'm not sure it's a question, so I'm not going to answer it. But if there's time, he can elaborate. But let's look at Chris's question, which is the unless goal imposes constraints on which methods are considered based on the current goal system has. You explore the use of state-based constraints on methods. Well, that's what the conditions, there's a conditions field. It's just like the conditions field in HGNs and HGNs. So for sure, that's there. But yeah, we've got both of them. Okay. Matt, is the only difference between problems and goals that goals are one literal and problems are multiple literals? Yes, and that of course that they can share arguments. That's the key idea. In terms of the notation, the HPN syntax, we always have a single goal in the head, but what it stands for is one goal potentially among many. And the way the interpreter works is that when you do the decomposition, you don't have a goal stack, right? You have a problem stack. And if you decompose things, you create new subproblems with multiple goals. And that is what gives you the ability to do the testing on whether or not an unless goal is unsatisfied, is present but unsatisfied. And again, you can do this. You can extend HGNs to handle this. You can have control rules. In fact, you look at something like Prodigy or SOAR, they've got control rules can impose goal ordering, but they don't have it all in one place like we have in the HPN methods. And I, again, believe this is going to make it much easier to support rapid learning from single training cases than the more traditional approaches. But we will see.